Okay, there we are. That wasn't too bad. Hey guys, welcome back. This is, of course, Calc 1. We are on our second to last day of class, and we're pretty much through the material. So this is where I want to pivot to kind of preparing for the final. So that's what we're going to do today. We're going to talk a little bit about the final exam. We're going to talk about the things that you want to make sure you're ready for, and then we can spend some time solving problems of whatever type you guys would like to solve. There's also one or two little concepts that I would like to discuss, kind of wrapping things up, but I will make that short and sweet. Alrighty, so here we go. All right, so today I'm going to talk about there's two different kinds of mean value theorem. So I'll be silly here and we'll say we're going to tell it a tale of two MVTs. You may or may not remember, we did talk a little bit about the mean value theorem way back in chapter 4. So that'll be fun. And then we're going to talk a little bit about prep for the final. And remember that your final exam for your section, is on the 28th at 8 a.m. And that's going to go basically the same way all of our other exams have. So I'll post a link probably around 7:30, 7:45, and you guys will want to join that a couple minutes early if you can to get things squared away. We'll be using Honor Lock and Zoom. I'll put you into breakout rooms, and the test will be in Canvas with all the same parameters as our regular midterm tests. So you'll need to answer the true, false, and multiple choice questions right there, and the free response questions you'll work on your paper. You'll type your final answers during the test, and then you'll upload things at the end. Let's see. Is there anything else I want to say about this right now? Don't think so. Of course, the final is cumulative. Covers everything. Is there anything else we need to say about the final? It's 2 hours instead of 75 minutes. So it'll be from 8 to 10 a.m. rather than like 8 to 9:45 or 9:15 or whatever. What else? Oh, the distribution. I think there's going to be around 20 questions. I went through it the other day. I went through my old final the other day from this class. I think it had 21 questions, something like that. So somewhere around 20 questions, depending on what I feel is necessary to add or emphasize or remove. Anything else here? No, I don't think so. I think that's about it. Oh yeah, up here with the tale of two MVTs. Let me also talk briefly about something called Newton's method. So those are both going to be quick little concept talks. You may recall that the mean value theorem it was something we talked about briefly when we first learned about the derivative, but there's only so many sort of questions I can ask you related to it. So it's not something we drilled on a whole lot. This says if f of x is continuous on the closed interval a, b, and differentiable on the open interval AB, then there exists a number C between A and B satisfying f primed of C is equal to f of B minus f of A over B minus A. This is the mean value theorem. And the picture that goes along with it, see, it's always a little bit tough to get a picture like this to come out just right. Says if you take an interval like A to B here, say, and you look at the secant line for this function f on that interval. Remember what secant lines are. That's the line that gives you the average rate of change as its slope. It's a line that connects 2 points on the graph. That's this guy, right? The slope of the dotted line is this guy. And remember that the derivative represents slopes of tangent lines. So what MVT is saying is that if you specify a secant line, I can find somewhere on the interval here a point where the tangent line is parallel. Here it appears to be right around here. All right, here's a point where the tangent line is parallel. This has a bunch of different interpretations. I think when we first talked about this, I said something about a trip to Miami or a trip to Orlando. If you measure somebody's average speed, like if a cop sees me leave Gainesville at a certain time at noon, and another cop sees me arrive in Orlando at 1 p.m., that second cop could actually pull me over and give me a ticket, even if I'm going the speed limit when I arrive, by the mean value theorem, because it's about 100 miles from here to there. And if I cover that distance in an hour, that means my average speed, my average rate of change, this thing, which is the slope of this line, had to be 100 miles an hour. And even if I'm not going 100 miles an hour at that moment, even if the tangent line down here isn't that steep or the tangent line here isn't that steep, they can be certain that somewhere in between there was a moment where I went 100 miles an hour. So this is just one of the kind of rates of change interpretations of the mean value theorem. And there's a bunch of other ways to think about it. One of the other ways involves integrals. So just for the record, the only sort of questions I could ask you regarding this thing would be to find the number C, right? I could say, okay, here's a function f of x, it's continuous on this interval and differentiable on this interval. Calculate the average rate of change. Find the point C where the derivative is equal to the average rate of change, that sort of thing. It's a neat concept, and it's really useful when you're trying to prove things. So if you were to go on and take a slightly more advanced mathematics class, like an advanced calc or real analysis class, the mean value theorem turns out to be a really important tool. I said this was going to be a tale of two MVTs. So the other MVT is an integral statement of the mean value theorem. And this is why we had to wait until this moment to have this talk, because you need to understand both derivatives and integrals. I think it's actually in your textbook. Find it. it was, yeah. So this seems to have some gentler hypotheses. The function f only needs to be continuous on AB. No statement about differentiability. And they say if f is continuous on AB, then there is a number c in the interval AB, like between A and B, satisfying f of c is equal to this thing. What is this? Why is that the case? So let me go ahead and copy this down. Talk about it. It says if f of x is continuous on the closed interval AB, then there exists, or there is a number c between A and B such that this time it's f of c, not f primed, is equal to 1 over b minus a times the integral from a to b of f of x dx. And the reason I'm excited to present this to you today is because I think understanding the connection between these two things is a great way to test your comfort with the fundamental theorem of calculus. So let's look at the parts of the second mean value theorem and see if we can try to see the first mean value theorem hiding inside of it. I claim that these are really equivalent. If you assume this, you can prove this. If you assume this, you could prove this. They both start the same way. We need our function f to be continuous on the closed interval AB. That means the graph needs to be one connected piece. The first MVT assumes that f is differentiable on AB. Where does the differentiability condition go here? What's special about the second version here, the mean value theorem for integrals, that doesn't require talking about differentiability? Let's kind of compare the pieces. Here you have f primed of c, here you have f of c. Here you have an average rate of change, or the slope of a secant line. Over here, what you have is actually, it's called the average value of the function f of x. And you'll learn more about that in Calc 2. But you take the area bounded by f from a to b, and you divide by the length of the interval. You multiply by 1 over b minus a. B minus a is the length of the interval ab. So you've got this b minus a factor downstairs in both. And then instead of having f of b minus f of a, you have this. What does that remind you of? What's the relationship between f in this second version and f in this first version? No wrong answers here. Just want to hear what you guys think.
Well, you have f prime of c is equal to f of b minus f of a over b over a.
Yeah.
Or b minus a. And then the other one is the integral of that, where f of c has not been differentiated yet. And so you have the integral.
That's a really good observation. That's the main thing. So over here we have, where it's really a statement about f primed, right? It's saying, you know, under the right conditions, something is true about f primed. And over here, we're saying under the right conditions, something is true about f. Well, this is an antiderivative for this, right? F primed is the derivative of f. That's normally the way we think of it. But f is an antiderivative for f primed. And this, we know by the fundamental theorem of calculus, is very much related to antiderivatives. It's an integral. Sorry. Oh, I gotta answer this. I'm sorry. Hello. I noticed. Oh my God. My internet keeps dropping. These motherfuckers, I get kicked out of class all the time. It's awful. So I'm trying to get this fixed. Yeah, is it 3 p.m. yet? No. Motherfuckers. To confirm, press 1, otherwise we won't show up. All right. It's an antiderivative. This is like an antiderivative for f primed, and the integral over here is like an antiderivative for this. In fact, if capital F were an antiderivative for little f, let's think about this. So think about this, assuming capital F is an antiderivative for little f. We'll call this equation 1. We can evaluate the integral in 1, and that would get us f of c is equal to 1 over b minus a times, if capital F is an antiderivative for little f, then this integral would be capital F of b minus capital F of a. So here what we would have is little f of c is equal to capital F of b minus capital F of a over b minus a. And this really is the same thing as the first MVT. So you can use the fundamental theorem of calculus, specifically FTC part 2, to reduce this equation here in MVT for integrals into this equation here, which is just a rewriting of the regular mean value theorem. It's just that instead of having a prime over here and the original function there, you have the original function here and antiderivatives here. Really genuinely the same thing. So that's the first thing, right? The mean value theorem for integrals actually says the same thing as the regular mean value theorem. You just kind of need to think about it through FTC2 in order to reduce the statement in MVT for integrals into the equivalent statement that looks like regular MVT. The other question I'd like to ask is, where does the differentiability criterion go? Why doesn't this guy need f to be differentiable?
Because it's continuous?
It's true that f is continuous here, but remember, it's possible to be continuous without being differentiable. So there is something going on here related to continuity. If you integrate a continuous function, what kind of function do you get? Think back to FTC1.
A differentiable?
Yeah. Remember that in FTC1, I won't go back to the book. In FTC1, it says if little f is continuous, then the integral from a to x of little f is differentiable, and the derivative of that integral is the original function. So by assuming that f is continuous on a, b, the kind of object that's being discussed here, you can think of, the way you prove this is you look at the integral from a to x of f of x dx. You treat this thing as a function of the upper bound. If you do that, then by FTC1, this is actually a differentiable function, and you can differentiate both sides and reduce it to the original mean value theorem. So again, the fundamental theorem of calculus, part 1, is what allows us to relax the differentiability condition to a continuity condition. So the connection between these two things, I think understanding the connection between these two theorems is one of the best tests of your comfort with the fundamental theorem of calculus. And I think it's a really nice thing. The second MVT is not officially a part of the course here at Santa Fe. This is not something I'm required to show you guys in this class, but I wanted to show you guys because you put in all the work to understand the fundamental theorem of calculus. This is probably the most important theorem related to differentiability. The mean value theorem is probably straight up one of the biggest theorems in all of differential calculus. So it's really nice to see it connected to one of the most important theorems in integral calculus. And of course, the mechanism to going back and forth between differential calculus and integral calculus is the fundamental theorem. Okay. Questions on this? Anybody want to ask or talk about anything else here? Like I said, it's not a great source of problems. I'm not going to quiz you on this too hard. Again, the only thing I really could do is ask you to find the number c from the first mean value theorem by specifying a function at an interval. But if there's anything else you guys want to do or say here, I'd be happy to do it. Okay. I invite you guys to look at the section in the textbook where this shows up. It's in 6.5. And they talk about this concept called the average value of a function. If you're interested at all in statistics, then this will be a big deal for you. The other thing I wanted to talk about, kind of buttoning up theorems, is Newton's method. Has anybody seen the proof that the square root of 2 is irrational? Is anybody familiar with that?
No, I haven't.
So it's a little bit number theoretic. I'll walk you through it really quick. So claim, well, we'll call it theorem. Square root of 2 is irrational. What does it mean to say that a number is irrational? Like, what does this word mean?
There's going to be an infinite amount of numbers after the decimal point, so it doesn't. We can't calculate a definitive point for it, where it ends.
That's a fine way to say it. If you try to represent the thing in decimal notation, the decimal representation goes on and on forever and doesn't have any nice repeating patterns. So if I raise 2, I take 2 and take the square root, is that going to work? No, I got to do it in the other order. If I take the square root of 2 and ask for a decimal, I get this thing, and a more powerful calculator can give me more and more and more decimals, but there's no nice patterns here. But what is that? What's the connection to the word rational? So irrational, whatever that is, should mean not rational, right? An irrational number, so quick note, a rational number certainly on the one hand, a rational number's decimal expansion will either be finite in length or have a repeating pattern. Like 1/3, the decimal representation for 1/3 is not finite in length. It's 0.333333 on and on forever. But it does have a definite pattern, right? It's just 3s. In fact, if you take any repeating decimal, or even if it has a block of repeating digits like 1.1818181818, those are all rational numbers. But the definition of a rational number is one which can be expressed in the form A over B, where A and B are integers, whole numbers. So a rational number is a number that can be written as a ratio fraction of whole numbers. And an irrational number then is one which cannot be written that way. So when we say that the square root of 2 is irrational, one way of interpreting that is to say, yeah, the decimal representation goes on and on forever with no repeating patterns. But really what we're saying is that this number can't be written as a nice fraction. Can't be written as like 5/3 or something like that. There's no fraction where the top and bottom are both whole numbers that is equal to the square root of 2. That's actually the definition of a rational number and an irrational number. The decimal notation concept is a consequence of that. Something you'll prove in Calc 2, by the way, is that every repeating decimal, regardless of the length of the repeating string, like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, is a rational number. It's a trick you use power series for. Not power series, you use infinite series for. So if you want to prove that a number is irrational, generally that's a little bit tricky. And then calculating irrational numbers is also very tricky. Like if I wanted to, how do I know that the square root of 2 is like 1.4, blah, 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 blah. Where do I get the 1.4? How does my calculator know that the square root of 2 is 1.412, blah, 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 blah? That's going to come down to something called Newton's method, which I'm going to show you in a second. So let's go ahead and run through the proof here, because if you've never seen a number theoretic proof before, these are quite beautiful arguments. The way this works is we're going to assume the contrary. We're going to assume that the square root of 2 is rational. Assume that the square root of 2 is equal to a over b. And I'm going to add one extra thing here. I can assume that this is also in lowest terms, meaning a and b have no common divisors. In other words, I've canceled everything here. Right? If I give you a fraction, you can always write it in simplest terms. You can always cancel out any common divisors between the top and bottom, right? Any common factors. So I'm going to assume that the theorem is false. I'm going to assume that the square root of 2 is a rational number and that its simplest form is a over b. Then squaring both sides, we get 2 is equal to a over b, right? But this is equivalent to saying that a is equal to 2b, or 2b is equal to a. Everybody with me so far? So I just multiplied both sides here by b, and that gives me this. Well, if a is equal to 2 times b, that means a is divisible by 2. A has a factor of 2. The way this is going to work is we're going to show that b also has a factor of 2. And that's going to contradict that these things have no common factor. So if we return back here with the assumption that a is equal to 2b, let me actually, it's been so long since I've seen this. There's a cleaner way and a nastier way to do this. I believe I forgot this. Rationality of root 2. It's not unique factorization. Oh, that's right. Yeah. No, I wrote something down wrong here. Sorry, we squared both sides, right? Yeah. I knew something felt wrong. We squared both sides. A squared over b squared. Right, this is how we got here. We took this relationship and squared both sides. So this means 2b squared is equal to a squared. So a squared has a factor of 2. So how is it possible for an integer, the square of an integer, to have a factor of 2? If you think about this, it actually means that a contains a factor of 4. So if the square of a number is divisible by 2, that means that the number a itself has a factor of 2 in it. And so the square of that number actually has a factor of 4. So the cleanest way to phrase this, factorization for nothing. Oh, what occurs the same number of times our factor 2 appears as an odd number. Right. Okay. So if a squared has a factor of 2, by prime factorization, we can assume we know that a can be written as a prime raised to a power times another prime raised to another power times another prime raised to another power. This is the fundamental theorem of arithmetic. It says that every integer can be written as a product of primes. One of these must be 2. So if the original number, if the number's square is divisible by 2, then that number's prime decomposition must have a 2 in it. So let's say P1 is equal to 2. Then A is equal to 2 times some other stuff. So A squared is equal to 4 times some other stuff. So I can come back here now and replace this A squared by 4 times some other stuff. Dividing both sides by 2, you see that B squared is equal to 2 times some other stuff. So now 2 divides B squared. And the same argument that we used here, since A squared has a factor of 2, we know that A's prime decomposition has a 2 in it. We now learn that B squared has a factor of 2, i.e. B squared is a factor of 2. And we know that this means, hence, 2 divides B. But that's it. We know that 2 divides A. In other words, A has a factor of 2, right? One of the prime divisors of A is 2. And we know that 2 divides B. Since we've shown that 2 divides both A and B, we have contradicted this assumption that A and B have no common divisors. And this is a mechanism of proof that, oh, sorry, wrong way. This is a mechanism of proof that you'll actually see pretty often. You assume that your theorem is false. Assume that the number square root of 2 is rational. And this comes along with the assumption that A and B have no common divisors, because any rational number can always be written in lowest terms. But then as a result of those assumptions, right, this one is that our theorem is false, and this one is a natural consequence of that, you arrive at a contradiction. You arrive at this idea that, okay, if 2 is rational, then A and B have a common divisor. But that's contrary to this consequence of 2 being rational. So that means that one of these assumptions must have been wrong, right? Either the square root of 2 cannot be written this way, or rational numbers cannot be assumed to be written in lowest terms. But you can always write a rational number in lowest terms. You can factor the top, factor the bottom, and cancel anything out. So the assumption that must have been wrong was that the square root of 2 could be written this way. So this contradiction, thus square root of 2, cannot be written as A over B for integers A and B. And that's the good stuff, right? So arguments like this are called proofs by contradiction. And we made use of some number theoretic facts in here, like that you can write a number as a product of powers of primes. There are ways to slim this down, but the basic idea is that if the square root of 2 were rational, then there's no way to write that rational number in lowest terms. But every rational number can be written in lowest terms. So the assumption that the square root of 2 is rational must have been wrong. So how do you calculate the square root of 2? How do I find those decimals? So if root 2 is irrational, how can we find the decimal representation? There's a bunch of ways. But given that this is a calculus class, the nicest one to talk about, especially in Calc 1, is Newton's method. You might guess this is pioneered by Isaac Newton. And the basic idea is to try and approximate the root of a polynomial. So we can find a polynomial whose roots, one of whose roots is root 2. So let f of x be equal to x squared minus 2. We know that this has the square root of 2 as a root. We know that f of x equals 0 if and only if x is 1 of plus or minus the square root of 2. All right, what does the graph of this function look like? Looks like this, right? It's this parabola shifted down 2 units. So the x-intercept over here is at negative root 2. The x-intercept over here is at positive root 2. The way Newton's method works is you start with a guess. You start with some x value that you think is close to the square root of 2. I'm going to just be silly about it, and we'll say 1. So here's the algorithm for Newton's method. find a function. So this is a tool for to approximate the number, what do we want to call it? Approximate the number n. So first you find a polynomial, which I shouldn't call it n, let me call it y. Find a polynomial with y as a root. Like here, I want to approximate the square root of 2. So I cooked up a polynomial that has the square root of 2 as a root. Then you guess at the number y. So for example, here I have maybe no better guess for the square root of 2 than 1. Assume I'm really daft. I think the square root of 2 is just the number 1. Then you take this guy and you find the point on the graph at your guess. You construct the tangent line to your function. Let me see here. Let's see. This will say, construct the tangent line to your function at that point, at that guess value. And you see where that hits the x-axis. Remember when we talked about linear approximation? This is kind of similar to the linear approximation business. So this would be my first guess. And then the place where that tangent line hits the x-axis, that would be my second guess. And notice that this is going to be actually a little bit closer to the true value than my first guess. And then you take this guy up here, you go back onto the graph of your function, you construct the tangent line there. And here, my resolution drawing this is finite because we're drawing by hand. That would be your third guess. So you guess at the number y, construct the tangent to f of x, I guess the number y. Let me call this first guess x1. So you construct the tangent to f of x at x1, and then you update your guess to the root or x-intercept of the tangent line. And this new thing would be x2. So there's a way to write down a formula for this. And there are some really cool pictures. I think the way the book presents it is a little bit hard to read, but I like the way Wikipedia does this. So let me show you here. So this is your formula, right? Your next guess is going to end up being your previous guess minus the ratio of the function at the previous guess divided by the derivative at the previous guess. And this really does come from the intersection of the tangent line with the x-axis. So let me see, we've got pictures here that are quite good. Here we go. So here's your first guess, tangent line. Tangent line hits the x-axis, that's your second guess. Tangent line hits the x-axis, that's your third guess. Tangent line hits the x-axis, that's your fourth guess. Tangent line hits the x-axis, right? And you see the thing that we're zooming in on, the thing that we're getting closer and closer to here is the x-intercept or the root for the blue function. Very cool stuff, right? I bet if we look for a GIF, Maybe not an obvious one. Yeah, here we go. Is this going to do it? Oh, they're working in general here with an S. But yeah, this is the way Newton's method works, and it's really quite cool. So I would like to run through this just really quickly. The collection of these processes, what this gives formulaically, is that you start with a guess, x1. And then your next guy is always your previous guy minus the ratio of f and f prime, right? Make sure I'm getting the f and f primes right. Yeah. Oh, go back. Oh, I got to close it like this. Yeah. Okay. Yeah. F prime downstairs. So it's going to be your previous guess minus f of your previous guess over f primed of your previous guess. So let's see how this shakes out if I use this function to try and approximate the square root of 2. We need both f and f primed because we know that the slopes of the tangent lines are always coming from f primed, and there's this repeated construction of a tangent line. The proof that all of this boils down to this formula is just some symbol juggling. It's not really a lot of fun, but watching it work is pretty cool. Let's take 4 steps. So I'll need f primed. F primed of x here is just 2x. And I'll need to follow this recipe. So if x1 is 1, then when I plug n equals 1 in here, I get x2 is equal to x1 minus f of x1 over f primed of x1. Since x1 is 1, this is 1 minus f of 1 over f primed of 1. And what is f of 1? What is f primed of 1? Well, f of 1 is what you get when you plug 1 in here. It's 1 minus 2, which is negative 1. So this is 1 minus negative 1 divided by, what's f primed of 1? Well, f primed of 1 would be 2. So this is 1 plus 1/2, which is 3/2. So x2, my second guess, is 3/2 or 1.5. You know, maybe we'll even do this in decimals. Oh, I prefer fractions. When n is equal to 2, because we're looking for a decimal thing, if I plug n equals 2 into that formula, then this would be x3 equals x2 minus f of x2 over f primed of x2. So we get x3 equals x2 minus f of x2 over f primed of x2. Now x2 is 1.5. So this is 1.5 minus f of 1.5 divided by f primed of 1.5. And that's 1.5 minus f of 1.5 is 1.5 squared minus 2. Again, I'll go ahead and use some calculator goodness here. Figure this out. 1.5 squared, which is 2 1/4, divided by 2 times 1.5, which is 3. And if we crunch this out, we get 1.5 minus 2.25 divided by 3. This would be our second guess, which is 0.75. And now we keep going. N equals 3. So I would be getting here my fourth guess, x4. It would be x3 minus f of x3 over f primed of x3. And I plug in 0.75. You kind of keep jumping back and forth over the actual value. So we go too big, then too small. The next one will be a little bit too big. So x3 was 0.75. So we'll have that minus f of 0.75 divided by f primed of 0.75. So this is f of 0.75, we said would be 0.75 squared minus 2. It's going to be negative 1.4375. So this is 0.75 minus negative 1.4375 over f primed of 0.75, which is just 2 times 0.75. Which is 1.5. And if I compute this, we'll get our x4, or x5, our fourth step guess, the fourth thing from our first guess. So let's see what we get. I've got 0.75. The 2 minuses there would make a plus, and then I've got 1.4375 divided by 1.5. And here we're getting closer and closer to that 1.4 blah, 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 blah. So this is 1.708 blah, blah, blah. This is Newton's method, and it's a pretty cool tool. If we ran this a little bit further, then we would eventually get all of those digits, as many digits as you want of the square root of 2. And kind of its first step is very similar to that linear approximation thing we did. That's really what's going on here. But we can improve. We can get better and better and better. So Newton's method and MVT, two cool things, cool tools that we use with calculus in order to evaluate, approve, or approximate things. There's one more cool thing about Newton's method here, and that's if you're interested in fractals. You can think of functions as taking in inputs that are real numbers. You can think of functions as taking in inputs that are complex numbers. Let's return to this picture really quick. All right. So our first guess was 1. That brought me over here to my 1.5. And then my second guess here brought me in even closer, and then third and fourth. If I'd made my first guess way over here, imagine that I had done that, then that tangent line would have sent me way out here. And then I would have come up here and then back in. I would have started zeroing in on this point rather than on this point. Newton's method works as long as your first guess is reasonably close to the thing you're trying to get to. If you think of these functions as taking their inputs from the complex plane, then you can color the complex plane according to whether or not Newton's method works with that first guess. That's what this is an image of. So each of these red, green, and blue regions is a subset of the complex plane. And if you feed this into Newton's method for a particular function, in this case, z cubed minus 1, then it will start taking you towards one point in the plane. The red regions will all go to one point eventually. The green regions will all go to one point eventually. And the blue regions will all go to one point eventually. In fact, the center of those kind of big blobs, you can kind of see an equilateral triangle in here. They're called cube roots of unity. So the red regions, if you start with a Newton's method guess from like this little red region here, you will eventually, through Newton's method, end up over here. Or if you start with a guess from this green region here, you'll eventually end up at a particular point over here. So you can take the complex plane and split it up into regions based on where Newton's method lands you. And it turns out this generates some pretty cool fractal shapes. They're called Newton's fractals. They come from Newton's method. All right, gang, that really is everything I could possibly want to show you in Calc 1. Genuinely, that's the whole game. So the rest of the class, I would be happy to spend taking questions in preparation for the final. Our last class on Friday will be all review for the final. So if there's any homework problems you would like to see, either from this week's homework or anything lingering earlier in the semester, I would be happy to take those now. Is there anything you guys would like to see? Anything we're stuck on, frustrated with, worried about on the final?
Like in the beginning of this class, we did the like limit, but with the h minus a something.
The definition of the derivative, yeah.
Yes, and like there's a shorter way by just taking the derivative. I remember on like test 1, you want us to do the long way. Do we need to know the long way or?
Yes, you do.
Okay.
I don't know if I've ever written a Calc 1 final that didn't have at least one of these on it. So I would say yes, you do need to be comfy with this definition. And we need to be capable of calculating the derivative using this definition. I promise I won't make you do it more than once on the final, but I will probably make you do it at least once. Can
we go over a problem like this?
Sure. What would you like to differentiate using the definition?
I don't have a specific problem in mind.
Well, some of these are easier than others. We could start with something like find f prime of x, where f of x equals x squared using the limit definition. So we know what we're going to get here, right? We're going to get 2x. But by definition, it's the limit as h goes to 0, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of, what is f of x plus h? Well, if f of x is x squared, then f of x plus h is x plus h all squared. And then f of x is just x squared and h is just h. So this would be lim h to 0. I'm going to FOIL this out now, and I get x squared plus 2xh plus h squared minus x squared all over h. You can tell me what to do from here.
You can cancel the x squareds.
Yeah, these guys are going to eat each other up. So I have lim h to 0, 2xh plus h squared all over h. How do I take this limit?
You can factor an h out.
Very good. And that's the game with all of these, right? Is to eventually factor an h from the top. because once you factored it, you can cancel it with the h from the bottom. So we get lim h to 0, 2x plus h. You could write this as over 1 if you want, right? When we cancel the h from the bottom, we just get a 1. So what is this limit?
2x.
Yeah, as h goes to 0, I just get 2x plus 0 over 1, which is just 2x. So we're done. Some other things from chapter 2 that you might want to remind yourselves of, because it has been a while and this stuff does come back on the final. Limit law work, right? And limits from graphs. These sort of things are very likely to show up on the final. The simple cases are simple, but many of them are not so simple. Remember this rapid oscillation thing, you can get in trouble with that. And then there can be challenges coming from graphs like these, where you've got holes, jumps, all sorts of wonky things that can occur. So make sure you remember how to do these. A really good move would be to work through some problems in the chapter 2 review. Right? These are all really good. Again, the true false in the chapter reviews are similar in their nature to the true false on my tests. That's just, it's how you write good true false questions related to calculus. So if you're looking for ways to practice those sort of things, the reviews are really, really good. Continuity can be a tricky biscuit. I know plenty of folks struggle a little bit with the definition of a continuous function, the difference between continuity and differentiability. Remember, continuous means connected, differentiable means smooth. You can be connected without being smooth, but you cannot be smooth without being connected. What else would you guys like to see? Oh, I'm sorry, I didn't notice there's some stuff showing up in the chat here. All right, so applied optimization, related rates, when is our final? What chapter should we focus on? So your final, it's on the syllabus, it's also in Canvas, is on the 28th at 8 a.m. It's 8 to 10 a.m. on the 28th. So it's exactly 1 week from today. It starts at 8 a.m. and it's a 2-hour test. Chapters focus on for the final everything. The final is cumulative. It covers everything, and the distribution is going to be pretty even because we've tested everything on the midterms. There isn't anything that's really been pushed to just the final. So I would recommend studying everything. But if you're wondering like what things do people usually get into trouble on the final, it's usually the chapter 2 stuff. Chapter 2 stuff is far enough in the past that folks tend to forget it a little bit by the time the final rolls around. So I would recommend going back to the chapter 2 review, but also studying all the past exams, studying all the homework, make sure you've done every bit of homework from the semester. And if I were taking this class right now, I would, between now and the final, grind out the chapter reviews in the book for chapters 2, 3, 4, and 5. All right, so we want to look at some applied optimization and some related rates. Let's do it. I guess we can do related rates first. That's 3.9. Nope. Just use these controls. Okay, well, it's a fun related rates problem. Like number 8 here. This is a good difficulty problem. It's not too easy. It's not too hard. So they tell us that if we have a triangle with side lengths A and B, and the contained angle is theta, then the area is 1/2 AB sine theta. So this is true for not necessarily right triangles. Maybe let's contain angle theta. So if you have a triangle like this, then the area is equal to 1/2 AB sine theta. You know, 1/2 base times height. Well, it turns out that this B sine theta is exactly how you find the height. If the altitude of your triangle is not super easy to read off, this works. So your area is 1/2 AB sine theta. And they want to know how would I say, if A is equal to, let's say, 8 centimeters and B is equal to 6 centimeters, how is the area changing if theta is increasing at some speed? I'm just making this shit up, but if theta is increasing at 2 radians per minute, 0.2, how is the area changing if theta is increasing at 0.2 rad per minute when theta is equal to pi/3. So you've got a triangle, side lengths A and B, contained angle theta, and theta is increasing. I want to see how the area of the triangle is changing at the moment when theta is pi/3, assuming that theta is increasing at 0.2 radians per minute. Classic related rate stuff. What is constant? What is not constant here? Can anybody tell me of the labeled quantities A, B, and theta, one of them that does not change over time?
A and B.
Yeah, A and B don't change, right? So you can kind of think of many versions of this triangle. I could draw it as A, as B, both still 8 and 6 centimeters respectively. So here's another version of this triangle. So theta is allowed to open up, and it's opening up at 0.2 radians per second. And the question is, what does that do to the area? If theta was all the way down here at 0, then the area would be 0. If theta were this tiny little sliver, then the triangle would have a pretty small area. But as theta opens up, the triangle is getting larger and larger in area, and the area follows this formula. So 1/2 is constant, A is constant, B is constant. What things are not constant in this expression?
Theta.
Theta, good. What else? These are constant, not constant.
Area.
Yeah, the capital A is also not constant, right? As theta changes, the area changes. So both capital A and theta are implicit functions of time. So what we're going to do is apply the differential operator d dt to both sides. In other words, we're going to differentiate on both sides with respect to t. On the left-hand side, I get dA dt, which is the rate of change for the area. On the left-hand side, I get 1/2 AB cos theta times d theta dt. Think of it as a chain rule. The 1/2 AB, you can just ignore those. Those are constant. But if you differentiate sine theta with respect to t, you differentiate the outer function. That's where your cosine comes from. The derivative of sine is cosine. And then you have to multiply by the derivative of the inner function. Well, the inner function is theta. The derivative of the inner function is d theta dt. So this piece here, this is really just coming from the chain rule. So if A is 8 centimeters, B is 6 centimeters, how fast is the area? Theta is increasing at 0.2 radians per minute. What is this 0.2? Which piece down here should I have 0.2 plugged in for?
d theta dt.
Good, it's the rate of change for theta, which is d theta dt. So I get dA dt is equal to 1/2. We said that A is 8 centimeters, B is 6 centimeters. I'm just making those up. Cos theta is the cosine of pi over 3. And d theta dt is 0.2. If this was a physics class, they would beat me over the head for not writing my units, but it's a math class. We can use dimensional analysis to determine what the units should be. This is radians per minute. This is unitless. These are each in centimeters. So this is centimeters squared per minute, which is dA dt. Very nice, right? dA dt should have the units centimeters squared per minute. It should be an area over a time. So centimeters squared, that's an area per minute, that's a time. Radians are usually thought of as unitless. And the cosine of pi over 3 is certainly unitless. So now we just have to crunch this shit out. 1/2 times 8 is 4, 4 times 6 is 24. So all of the numbers out front are 24. What is the cosine of pi over 3?
1/2.
Very good. Times 0.2. 24 times 1/2 is 12. So this is 12 times 0.2. All right, like this so it's clear. We're multiplying those, not a string of digits. How did I close Wabbit? I guess we could have sussed this out.
It's 12 times 0.2.
Oh, thank you. Sorry. Yeah, of course it is. Yeah, okay, 2.4. So this is 2.4 centimeters squared per minute. That's how fast the area is changing at that moment when theta is pi over 3. The trick is to remember not to plug in stuff until the end. All right, if you plug in before you differentiate, you can get into trouble because then you end up treating things that aren't constants as constants. So first you differentiate your algebra relationship. Sometimes that will be given to you like it was here. Sometimes you have to come up with the algebra relationship. So here they gave us this, but not always will that be the case. So really, usually our first step is to draw a picture and then to come up with something like this, an algebraic relationship between the quantities in question. Then you differentiate implicitly on both sides with respect to time, making sure that you treat things that are constant as constants and things that are not constants as functions of time. And then you plug stuff in. Any questions on this example? We can do more of these on Friday if you want, but any questions on this particular one? Okay. We wanted to see an applied optimization problem. I think it's going to have to wait till Friday, though, because we are right out of time here. So Friday is going to be all review. Bring your questions, all right? Go over anything you want to see. Go over your homework, go over your past tests. Actually, with the exception of the most recent test, I still have some people who need to take that. Go over homeworks, old tests, study guides, whatever you want to see. You can look in the chapter reviews of the book. I really encourage you to do that. You can bring questions on Friday from those. And then Friday will be all day your class. So we will just study for the final. Any problems you guys want to see. And then remember your final is 1 week from today. It's at 8 a.m. I'll post some announcements to Canvas, but I really encourage you to put that in your phone right now with an alarm at least an hour ahead of time to remind yourself what's going on. Any burning questions before I let you guys go? Okay, guys, have a good afternoon or a good rest of your day. I'll see you on Friday.